See, 2 days ago on Wednesday, we spent some time with a couple demonstrations looking at what happens when a wave encounters a boundary, when it encounters a new medium. It's coming from air to water, or it's coming from slinky to somebody's hand. We know that there's two things that can happen when a wave encounters a boundary between two materials. And we know that those two things always happen. Both of them always happen, one more than the other, but those two things that can happen are transmission and reflection. Reflection is bouncing back. Transmission means it keeps going. If the two materials, the two mediums, are very, very similar, then we're going to get most of the wave transmitting. Most of the wave is going to keep going. But if the materials are very different from one another, then most of the wave is going to reflect. And that's what we saw with our demonstrations on Wednesday. The materials were very different from one another. The first one we did was the wave went down a slinky and it went into somebody's hand. So slinky, person, two completely different media. Most of the wave reflected, only a little bit transmitted. The next demonstration we did, the slinky wave was going down the slinky and then to air. Slinky, air. Two very different mediums, mostly reflection and only a little bit of transmission. The part of the wave that reflects can reflect either right side up or upright or upside down. It will be reflected right side up if the medium that it's coming from, the slinky, is not attached to the new medium. Slinky to air, there's no attachment there, right? So it reflects right side up. If the slinky is attached to something, right, you're going from something that's slinky to something else that's not attached to it, sorry, that is attached to it, then it's going to be reflected upside down. So we're going to say here that it's going to be reflected right side up when it's not attached, and we're going to say that it's reflected upside down when it is attached. The demonstration we did on Wednesday, we couldn't demonstrate with a slinky the law of reflection, which simply states that if you've got a boundary here between the two materials, and the wave is going in at an angle, look, we're still going to get transmission, we're still going to get reflection. If the mediums are very different, we're going to be mostly reflection, still going to be reflected right side up or upside down, depending upon whether it's attached or not attached. But it's going to be reflected at an angle as well. Draw a little normal line here, a line that's 90 degrees to the boundary. And if we label this angle between the normal line and the first ray as theta 1, then the angle between the normal line and the second ray, theta 2, will be equal to that. That's the law of reflection. You guys have all experienced that before, right? You're playing pool, and you know you want to bounce a ball. You want to bounce a ball off the bumper. You want the ball to end up over here. Okay, there's another ball in the way, though. You got to get it past. What do? You bounce it off like this. You know what the angle has to be because you know the angle of reflection will equal the angle of incidence. Theta 1 will equal theta 2. This is what happens to the reflected portion of the wave. Now, what happens to the transmitted portion of the wave? In the case of the demonstrations on Wednesday, there's not very much that was transmitted. And sometimes when the mediums are very similar, there's a lot that's transmitted. It's mostly transmitted. What happens to the transmitted portion of the wave, whether it's a lot of the wave or just a little bit of the wave? Well, there's a couple of things that will change, a couple of things that will either increase or decrease depending upon what the new medium looks like. The speed of the wave will change. Sometimes the speed of the wave increases, sometimes it decreases. If you've got light waves going from air to glass, then it slows down. The speed slows down quite dramatically. But if you've got light waves going from water to air, then the speed speeds up. The light speeds up quite dramatically. The speed will change. When you're going from one medium to another, the transmitted portion of the wave, the speed will change. Will either increase or it'll decrease. The wavelength will also change. If the speed increases, the wavelength will increase. If the speed decreases, the wavelength will decrease. Take a look at the universal wave equation that we learned the other day, right? As v goes up, lambda must go up as well. The direction can change. I'm going to star that one because the direction doesn't necessarily change, but it can change. I'll explain when it does and when it doesn't in just a moment. What stays the same? The frequency. Once a wave has been made, the frequency of the wave, no matter what, doesn't change. So if you've got a wave that's going straight into a new medium, so let's say this is the boundary between the two media. Here's my wave going this way, and it's going into the new medium straight on. It will change speed, it will change wavelength, it will not change direction. Remember I said direction will sometimes change. It can change. But when the wave is hitting the boundary straight on, it won't change. When does it change? When it hits the boundary at an angle. I'm going to draw a little analogy here. Call it the soldier analogy. You'll see this again next year in Physics 30 if you take it. We do this in more detail next year. This is a boundary between two materials. The first material is going to be pavement. It's a parking lot. The second material is going to be a swamp. For whatever reason, I don't know why, but for whatever reason, we have soldiers in this parking lot, and they're marching. It's a parade. I don't know. For some reason, there's soldiers in this parking lot, and they're marching. And you guys know when you watch soldiers march, they watch in stride, right? They go together like this. They all go together. Those soldiers are going to all go at the same speed. They're going to all go in phase with each other, so that a few seconds after this moment in time, these soldiers are all up here. Right? They're all marching at the same speed. They're all marching at the same pace, right? Oh, wait. This guy's not. This guy isn't quite as far as the other guys. How come? The first five guys are marching on pavement. He's in the swamp now. What happens to him when he goes into the swamp? He slows down. Right? If we're going the other way from swamp to pavement, he would have sped up, right? But in this case, he slows down. Let's draw a line joining them there. Let's go a few seconds later. Soldiers are up here. Well, the first three guys are up there. The fourth guy is into the swamp now, so he slows down. The fifth guy is into the swamp now, so he slows down. The sixth guy, well, he's still in the swamp, so he's still going slow. A couple seconds later, if we visualize these soldiers as being waves, they're not, but let's visualize them as being waves for a second. The wave was traveling in this direction. Now the wave is traveling in this direction. So when the wave hit a boundary straight on, it changed speed, it changed wavelength, but it didn't change direction. When the wave encounters the boundary at an angle like this, the wave changes speed, right? It's slowed down. The wavelength changed. Look, the distance between the waves here is pretty big. It's pretty small right here. The wavelength changed. But what else also changed? Look at the red line here. Look at the red line here. The direction also changed because of the difference in speed. What didn't change? What didn't change when we went from the pavement to the swamp? The frequency. Because once the wave has been made, the frequency will never change. Yep. Yeah, absolutely. That's a good question. If you didn't hear that, everyone, the question was, could I explain using the formula how the frequency doesn't change? Okay, so let's start a new page for that actually. So our formula V is equal to F times lambda. It means that V is directly related, directly proportional to F, and it's directly proportional to lambda. So that means that if something happens to one of these variables, something has to happen to one or two other variables. Notice I said one or two other variables. Okay, if wavelength changes, frequency could change, could go down and keep the speed the same. If wavelength goes up, frequency could stay the same and speed go up. If frequency goes up, wavelength could stay the same and speed goes up. Sometimes what happens in an equation is when we get one thing changing, one other thing changes in the equation. Sometimes a couple of other things change in the equation. In this equation, as speed changes, the wavelength changes, but the frequency doesn't. We can't justify why the frequency stays the same in terms of the equation. It's a fundamental aspect of nature where the frequency will always stay the same once the wave has been made. But we can justify using the equation why that's possible. Okay? If we said the speed was 10, the frequency was 2, and the wavelength was 5. What happens if the speed goes up to 20? Well, is it possible mathematically for a frequency to increase to 4? Sure, it's possible mathematically, but it doesn't happen because a fundamental law of nature says the frequency stays the same. But it is possible mathematically as well for the wavelength to go up and the frequency to stay the same. So the equation doesn't tell us why the frequency stays the same, but the equation tells us that it's possible for the frequency to stay the same. It's nature that tells us frequency has to stay the same. Does that make some sense? Does that stuff make sense? All right.